Okay, this is Dr. Williamson working another kinetics problem. Here it says in this problem, in a first order decomposition reaction, 45% of a compound decomposes in 10.5 minutes. Calculate the rate constant of the reaction. How long does it take for 90% of the compound to decompose? And if the initial concentration of the compound is 0.150 molarity, what is its concentration after 20 minutes? First thing we have to do is interpret the question to give us something to hang on to, right? It says a first order decomposition reaction, right? Well, what is a decomposition reaction? I've given some examples over here of decomposition reactions. Ammonia, NH3, and I typed it here. This is, right, NH3 decomposing into N2. It's supposed to be N2 plus H2. And this is 2H2O decomposing into H2 and O2. Okay, those are examples of decomposition reactions. We can write that in general as A decomposes into P products. And we don't need to know for now, for this problem, what this coefficient is. Because when we write the rate law, this exponent 1 is unrelated to this 2 here. And these 2's are just coincidence of the examples that I chose. So it's a first order reaction. We know that if it's first order, we know that, okay, first order rate is K A to the 1 power, which is what I wrote right here. Then it says 45% of a compound decomposes in 10 minutes. Here I'm wanting to know concentration over time. That means I need, when I talk about the rate law and concentration over time, whenever I want to know concentration over time, that's supposed to be a TIME. That's when I get the integrated rate laws, which I showed you guys before. That's how you figure out, rate lam, didn't mean to write rate lam, rate law. Okay, so that's how we interpret this. Integrated rate law. What is the integrated rate law for a first order reaction? That's this thing right here. Where again, I'm typing this. This is natural log A times T is equal to minus KT plus natural log of A naught. Right, I'm going to erase this, but I just want you guys, since I type a lot of this stuff in this software, I want you guys to get used to seeing that. Okay, so again, first order decomposition reaction. Here are some examples of decomposition. And if it's first order, I write this. I don't have to know what the exact chemical reaction is. I just know it's first order. I can write a symbol, whatever it is. It's chemical A is what I'm going to call it. And it's decomposing first order. And I want to know concentration over time. Oh, that's code talk for it. Use the integrated rate law to solve these problems. This is the integrated rate law right here. Okay, guys? Now, something I'm going to remind you of, when you use integrated rate law for first order reactions, this equation right here is really tricky and hard to use correctly. Don't use this when you solve problems for homework or for the test unless you're doing graphing. If I massage this or rearrange the algebra, I can rearrange it into this form. Natural log of AT over A naught equals minus KT, or AT equals A naught e to the minus KT. I demand that when you do calculations with percent or ratios, you use this form. Don't use this. And when you're calculating for first order integrated rate law for concentration values, I demand that you use this form. If you use this, you're going to mess up. Okay? So I'm going to show you guys how to do that. What I'm going to do is I'm going to erase this stuff here. Get rid of that. Okay? Get rid of that. What do these things mean? AT means the concentration of A at any point in time. A naught is the initial concentration of A, meaning at the beginning of the experiment or the beginning of whatever you're doing. That means at time t equals 0. K is the rate constant. T is the time, typically measured in seconds or minutes. Sometimes you'll see it in hours. Okay. So here in a first order decomposition reaction, 45% of a compound decomposes in 10.5 minutes. So we're calculating in 45%, that's a ratio. Percent means per 100. It's a ratio. We're not going to use this form. We're going to use this form. And 45% decomposes in 10.5 minutes. That means AT is equal to 55% of the original amount after 10.5 minutes. Or in other words, when I put it in here, AT is equal to 0.55 of the original amount. How come? Because 100 minus 45, I have only 0.55, well, 0.55 of it left. So what I'm going to do is I'm going to erase this stuff because I need the space. And I'm going to write the natural log of 0.55 A naught over A naught is equal to minus KT. I'll substitute for T in a minute. But that's what that means when it says 45% of a compound decomposes in 10.5 minutes. That means that AT has become 0.55 of the original amount. The A naughts cancel out. I don't know what the original amount was, but I know that they cancel out. When I rearrange the algebra here, I'm going to have K is equal to minus the natural log of 0.55 over 10.5 minutes And when I do the math, I'm going to get K equals 0.0 0.0569 minutes minus 1. That's A, the rate constant. So for A, we got K is equal to, let me type it. Text. I'm going to use small font so I can save some space. Type it right here. K is equal to 0.0569 minutes to minus 1. Now I have a record of it, but I still have space. That's part A. Erase this stuff. So we did part A. Part B, how long does it take for 90% of the compound to decompose? That means when 90% of it decomposes, the amount of AT is equal to 0.1, 0, and 90.0. I should do this. I should have done 0.4. I should have done 0.550 in the previous problem. I didn't. It was my mistake. But anyway, this will be 0.110 of the original amount. And here it says how long. So we're solving for time. Which equation I'm using? I'm using this one because that's the one you use for percents or ratios. So I'm going to take this equation. I'm going to rearrange it and solve for time. So I'm going to have T is equal to, got the minus sign, minus the natural log. I'm going to substitute this in 0.100 A naught over A naught. I don't know what the original concentration was, but I know these are going to cancel. Divided by K, the rate constant. And K happens to be 0.0569 minutes to the minus 1 power. The A naught cancels with the A naught. And I got my minus sign over here. So I'm going to have the natural log of 0.10. Make sure you use the ln, not the log. You'll get the wrong answer if you do that. And when I do that carefully, assuming I didn't mess up, I got 40.5 minutes. Okay. You have to do that. You can't use ratio and proportion. Sometimes I'll have students do this. Don't do this. This is wrong. Okay, let me do, let's do this. This is wrong. Let me show you this. This is wrong. Don't do this. Students will do this. They'll go 10.5 minutes over 45% is equal to X minutes over 90%. And then they'll solve for X. This is ratio and proportion. This is wrong. Don't do this. Why is that? Let me erase this stuff here. We got 40.5 minutes. Let me show you why that is wrong. Okay, make sure you know this. When this stuff decomposes, when chemical A decomposes, it decomposes with a curve. Let me draw it more curvy. Decomposes with a curve. Okay, so that is a exponential decay. That's exponential decay. When you use the ratio and proportion, let's say linear decay, that's that stuff, right? That's wrong, because that presumes, this right here presumes it goes down in a straight line decrease. That's what this is. Ratio and proportion assumes it goes down in a straight line decrease. Actually, chemical A goes down in this curvy line decrease, like that exponential decay. So the number that you calculated was this, but the reality was this. And when reality mismatches with what you thought it was, the technical term for the mismatch between reality and what you think is what we call being wrong. Okay, so don't use ratio and proportion. Let's go back to the last one. Let me try and delete this stuff here. Okay, and erase it without erasing other stuff that I want to keep. All right. And text, let me change the size of the text from being ginormous. All right, and go back to red font to draw. Go back to red font. The next one, if the initial concentration of the compound is 0.15 molarity, what is its concentration after 20 minutes? We don't use this one for solving this problem. It's for graphing only. Okay. This one here is for percents and ratios, and this doesn't have any implied percents and ratios. This is concentration, concentration. Okay, that means we're going to use this one because Dr. Williamson said so. If they just trust me, I'm not going to get into all the details, whys and wherefores and stuff like that. I can't prove all of everything all of the time. Okay, some stuff you just got to take my word for it. So we're going to use this and solve these problems. So it says, if the initial concentration of a compound is 0.15 molarity, what's its concentration after 20 minutes? That means we're saying, okay, what is the concentration of this at any time t? And that's t is equal to 20 minutes. So, okay, what's the concentration at 20 minutes? That's equal to 0.1, it's supposed to be a 1 out of L, 1,5 molarity times E. I'm trying, guys. E to the minus, and what did we say K was? 0.0569 minutes to the minus 1 power times, and T is 20 minutes. 0 minutes. The minutes cancel, which is good because we got minutes to the minus 1 times just plain minutes. And when I did this on my own separately, I hope I didn't mess up. I got 0.150 molarity E to the minus 1.14. And then when I do all of that, assuming I didn't mess up on my calculations, which since I'm recording it and putting it on the internet, it almost guarantees I messed up on my calculations. I got 0.0481 molarity. Okay. Okay, I had to pause the video for just a minute. But anyway, that's what I got there. And, I hope that helps. Again, when we do first order reaction calculations, integrated rate law calculations, just trust me, it's been my experience that using this is way too tricky. You'll mess up. So if you use this and you mess up, you're gonna lose points. I don't want you to lose points. Okay. Because I told you in lecture and here on video and in lab. You want to use this form. We're calculating with percents and ratios. And you want to use this form for calculating concentration values. Okay. Anyway, I hope that helps. Hope to do more problems for you later.